All right, this is a little bit more complicated version of that problem. It says find the value of x. Obviously, there's a y and a z also. Maybe we can find all three of them. But notice that it's the same picture we just saw a moment ago, except instead of having these two pieces known, we have that piece known. I don't know either of these pieces either, and I've got all these cool colors here to help you identify things. But x is only that part of the hypotenuse. X plus 5 is only that part of the hypotenuse of the big right triangle. 6 is that altitude measure. And the relationship between the altitude, the 6, and these two pieces, and if I apply that relationship, we know that the product of these two pieces equals that number squared, right? So again, if I apply that same rule here, it's going to look like this. 6 squared is equal to x plus 5 times x. This is not going to be as pleasant of a problem, but again, I'm using the exact relationship. Since x plus 5 and x uses the same letter x, it's a workable problem using algebra. All right? It's not going to be as easy a problem, but we'll see that when we get to it. So next, 6 squared is 36. And when I got x plus 5 times x, recalling from Algebra 1, we've got to distribute this x through the parentheses. So it's going to be x squared plus 5x, like so. And there's two types of quadratic equations. One we've been seeing all the time, where a letter squared equals a number, or can be made to look that way. It just has an x squared in it. Okay, and those are very straightforward problems. When it has just x squared, get x squared by itself, get the number by itself, take the square root of both sides, you're good to go. All right. The other type of quadratic expression has both a quadratic x squared term and also a linear x to the first power term. Those are a little bit more complicated to do. And again, this is something you would have studied in Algebra 1. That was last year, and you haven't seen this for a while. So I'm just going to refresh your memory back to Algebra 1. When I have a quadratic expression, something to the second power, and a linear expression in an equation, so there's an equal sign also, my first task is to get everything equals 0. So I want everything to equal 0. So to make that happen, I'm going to move the 36 over to the right. Positive x squared is better than a negative x squared, so the fact that x squared is positive says I want to keep x squared where it's at, I want to move everything to the side with it. So if I move the 36 over, I'm going to get 0 on the left-hand side equals x squared plus 5x minus 36. Okay, once you get everything equals 0, the next thing you want to do is you want to factor the quadratic expression. If you can factor the quadratic expression, all right? If you can't, there's other techniques, but for now, let's just make the assumption we'll be able to factor everything. If they start throwing stuff at us that doesn't factor, then we might investigate the quadratic formula. All right, so with factoring, the thing I'm looking at specifically in how I decide to factor a quadratic trinomial is the first term. If the first term is x squared and only x squared, nothing's being multiplied by it. Okay, which is what's happening here. The way we factor is we find two numbers that multiply to make this number, that also add to make that number. We're looking for a pair of numbers that does both things. They multiply to make negative 36. They add to make positive 5. They have to do both things, and the signs do matter. So I don't know if you guys already know the answer or not, but I'm just going to represent a chart here. Factors of negative 36. The sum should be positive 5. All right, let's pretend that nobody's figured it out yet. All right, if you have figured it out, just keep it to yourself. All right. So, in order to make a negative product, what's true of the signs and the numbers being multiplied? One negative, one positive, okay? If I want to add these two numbers together, I want to get a positive sum. Which number should be positive, bigger or smaller? Bigger. Okay, so if you don't know what the answer is, here's how you find it out using this chart. The left-hand side of this chart is your guess. You're making the product happen. And I start with the smallest number I can think of, 1, and I multiply it by whatever it takes to make that. And again, I want to make the bigger number positive, the smaller number negative. So 1 times 36 makes 36, make the 1 negative. Now, algebraic adding, if you're adding two numbers and the signs are different, should you add or subtract? If I want to add these algebraically and the signs are different, what should I do to the numbers? Subtract. And since 36 is bigger, it's positive. So if this number here happened to be positive 35, that's the magic pair of numbers. Okay, it's not 35, it is 5. So we keep going. Next number is 2 times 18. Next number is 3 times 12. Next number is 4 times 9. Okay. All I'm doing on this chart, all that I'm making happen is I'm picking this number each time. And then I'm just doing a little division. 36 divided by 1 is 36. 36 divided by 2 is 18. 36 divided by 3 is 12. 36 divided by 4 is 9. 36 divided by 5 doesn't divide evenly, so I wouldn't write it down. 36 divided by 6 is 6. So the next number on the list would have been negative 6, comma 6, 0. Okay. So I pick this number, I figure out what it takes to make the product be 36, and then I algebraically add the numbers. Negative 1 plus 36 is 35. Negative 2 plus 18 is positive 16. Negative 3 plus 12 is positive 9. Negative 4 plus 9 is positive 5, and so on. I wanted a positive 5, which is right here, which means that's my magic pair of numbers. All right, so again, that's how you can find that pair of numbers. Just a very nice little organized chart there. A little guess and check with a little bit of a pattern to it so that you can make sure you've gotten every single possible pair of numbers. And once you find that magic pair, you're going to group x with one of those answers and x with the other answer. And that's how we factor. All right. And again, this would have been in Algebra 1 last year, probably January. Right around that time of year. In January last year, Algebra 1 is about the time you probably hit quadratic equations and factoring quadratic trinomials. All right, so the next step after you factor, again, quadratic expression equals 0. Quadratic expression gets factored, so the product equals 0. The zero product property states that if you're multiplying two things and they equal 0, one of the things being multiplied has to equal 0. So what's being multiplied in this problem is x minus 4 is being multiplied by x plus 9. Those are the things being multiplied. Okay. The number 0 creates a product of 0. What's 0 times 8,947? 0. Does it matter that the other number is 8,947? No. So what's happening here is this number, x minus 4, is being multiplied by that number, x plus 9. If either one of these numbers equals 0, doesn't matter what the other thing is, the whole thing equals 0, right? So the zero product property states that once we get to this point, we either say that the first thing must equal 0, or the second thing must equal 0. That's the zero product property. And if x minus 4 equals 0, now we're into a linear equation. All we got to do to solve that is move the 4 over, right? So chop the 4, makes it positive. X equals positive 4 is one answer. Chop the 9, make it negative. 0 minus 9 makes negative 9 is the other answer. So there's the Algebra 1 portion of the show for today. All right, now we're back to geometry. We have two answers for x that are both accurate for the equation we created. We have a geometry problem over here. What does x represent? What's the x represent here?
That small portion.
Just that little small portion. It represents the length of a piece in a triangle, right? Lengths can only be positive. So positive 4, negative 9. Negative 9 doesn't make sense in the context of this problem. It's not a good answer. So even though all this work led us to this negative 9, which is accurate by the equation, the reality of the problem is that answer doesn't work in our problem. So we can throw that one out. Okay, we have to make those decisions sometimes. So what is the value of x? X must equal 4. Now, pretend this problem said find x, y, and z. So x equals 4. What does x plus 5 equal? 9. Right? Now that we know this is 9, this is 4, if I wanted to find out what z equaled, I know that z squared should equal something times something. Z squared equals the entire length, which would be 13, times the piece closest, which is 9. So z squared should equal 117. So z would equal the square root of 117, which my calculator says, square root of 117 is about 10.82. If I wanted to find out what y equals, over here, y squared equals. Y squared equals the entire length times the piece closest, right? So that'll be 13 times 4. 13 times 4 is equal to 52, so y should equal the square root of 52, which my calculator says is about 7.21. Both y and z, once I knew what x equaled, we're just that simple letter squared equals number structure, right? But again, since we had x and x plus 5, we get this term right here is what creates that whole technique there. That the x to the first power in that x squared problem creates that factor being necessary. So just keep that in mind that you did learn this last year. You haven't used it recently, so again, I just want to run through the whole technique very well with you. But again, that's something you should have learned last year. You should be practicing it and get better at it, so when it does show up, you're ready to use it. All right?